Okay, today we're going to do one more computation of the electric field of a charge distribution. We're going to start out with what we've already done, do the electric field for one charge, and then we are going to extrapolate that to the electric charge for an infinite charged plane, for a plane that goes out in every direction to infinity. We're going to find that we need two pieces of information. First is Coulombs Law, which you guys have now used many times. And the second is the superposition principle, which, just as a reminder, this is just a fancy way of saying that the electric field of 5 charges is the same as the electric field of each one of those charges all added up together. So you add up, you find the field for charge 1, and you add up fields to charge 5, and you get the total. So let's get started. Let's look at the electric field of one charge. We're going to do one thing that's a little bit different than we've done before. So far, we've done everything in 2 dimensions, x and y, in the x and y plane. What we're going to do now is I did forget something. But what we're going to do now is we're going to move to 3 dimensions. Before we do that, I just want to introduce just a brief change in notation. So what we've been using is that the electric field of one charge is given by this expression right here. Now I'm going to change it just a little bit, because what we're going to do is we're going to look at the electric field at some location r. And the r with a vector on it just means that it's x, y, z coordinates. So at some point with x, y, z coordinates at a distance from some charge, that would be the r, we would get an electric field. And then the r on the right-hand side is just that. It's just the distance from this charge to this point that we are measuring at, and in the direction that goes from the charge to this point where we are measuring. So it's just a very slight change in notation. So now that we got that taken care of, let's go ahead and move this to 3 dimensions. So now we have this charge, and we've got some point r, and I'm going to draw a few extra lines here, a few extra projection lines, just so you get an idea of what we're looking at in terms of the coordinates, so you can see in what I'm intending this drawing to be. So if we were to draw a line directly straight down along the in the direction of the z-axis, if we were to draw that from the point where we want to measure the field, this is what it would look like. Well, we can also draw that to the z-axis. So now this is how high above the xy plane we are, and then this is where in the xy plane we are, but that also means you've got these x and y coordinates. So you can see that we're at some point here where we have coordinates x, y, and z. And now there we go, x, y, z. Now we're going to go ahead and we're going to do something that will eventually make our life a little bit easier. We're just going to shift our coordinate system. Instead of having the charge be at the center or the origin be at the charge, we're going to have the origin be right underneath the point where we are evaluating the field. So we're just going to slide it over like that, and we haven't changed the position of anything except for the axes. So the distance is just the same. The XYZ is all the same, except that we have now translated. So now we are not at XYZ, but we are at 0, 0, and I'm calling it Z sub P, i.e. the Z at the point that we are trying to measure the field at. And then what are the coordinates then of this charge? Well, if we were at XYZ before, then, we were at xy 0 before with the charge. This charge is in the xy plane. So if we're there, we are now at minus x minus y 0, okay, because we've moved this around. All right, I'm going to leave it at that. I made a little mistake there in the sense that we used to have the origin right here, so this used to be at 0, 0, 0, but now we have moved our whole coordinate system, so now we're at minus x minus y 0. So that's where the charge is, but like I said, nothing physically has changed. All we've done is moved our coordinate systems. So now the question is, how are we going to go ahead and calculate what this field is? And you guys already know. We're going to use Coulombs Law to calculate what this field is. And so what does that trick become? Well, we know what Q is. K is just a constant, we know that, so all we need to do is figure out what this r squared is and what r hat is. And this is something you've done before. We're going to do it just a little bit different now, and we are in 3 dimensions now, so it's going to make it a tiny bit different. But we'll go ahead and we'll see what the implications of that are. So this vector r going from the charge to the point P, you can write it like this. And I would actually like you to convince yourself that this is true. If the x sub q, y sub q, and z sub q are the coordinates of the charge, and the x sub p, y sub p, z sub p are the coordinates of the point at which you're measuring, what I'd like you to understand and make certain you understand is that this expression right here is the expression that gives us this vector right here. It gives us a vector that is in the right direction. And I think you should be able to look at this and figure that out. You know we're going from the charge to the point. From the charge to the point. And because we are doing that, this is the expression that ends up being accurate for that. Well, in particular, all we're going to do now is just plug in these values for x, y, z for x sub q. So we're going to have a minus x here, we're going to have a minus y here, and we're going to have a minus z there. And, we're going to have a 0 here. And then what about the x sub p, the point? Well, here are the coordinates right here. We're going to have 0, 0, z sub p. Okay, so what does that end up giving us? What it ends up giving us is we have a minus x, a minus y, and a z sub p. Now, I kind of, just to make certain that you guys understand here, when we would, so the actual value of x that we would plug in here would be minus x. So for this particular vector, this would be minus x, and so this would end up being a plus x. So this is the general expression for what this vector would be, and then we would plug in the x and y's. And I'm sorry, I kind of misspoke just a moment ago because I wanted to keep this as the general expression, and you'll understand why in a little while. So now we've got that, though. We have this general expression for any location x, y, where this q is, as long as it's in the plane, the xy plane, and its z value is 0, we now know what this distance is, what the vector distance is, which of course means we know what, that's right, we need to keep that, which also means we know what the distance is. So the distance is just the square root of the sum of the squares of each of those values in the vector. So we now know the only thing left to get is the r hat. Now, what we've done in class and what we've done in previous examples is we've drawn the angles and determined based upon the angles that we draw. We've looked at the cosine and sines and determined what the r hat direction is. But you will recall we have another definition of r hat, which is just r hat is equal to a vector divided by the magnitude of that vector. So we can replace that in our particular instance. Our vector we have right up here, and remember this once again, this is a generic form for this. So for any xy value this works. And so for this particular point, we would put in a minus x in place of x. In other words, the value of x here is negative x, whatever that happens to be. And the same thing here with y, and z sub p is just the height above the plane at which we are measuring. Okay, so this is it. We have r hat. We have our r squared. We'll just take the square of this, and we'll have r squared. And we know everything else. And so when you put this all together, what you end up with is one expression, but 3 different components of the field. And I'm going to break into that just for ease of notation. We're going to take this information, and we have an e sub x, an e sub y, an e sub z. And that's it. We're done. And at this point, all you need to do is just put in the values. So, for example, if we are at x coordinate of minus 3 meters and we're at a charge of 6 microcoulombs, we would just put those values into this equation here, and there'd be some y of whatever, negative 4 meters, and some z sub p of maybe 50 centimeters, which we would then say is half a meter. just because, once again, we need to get all those units right. But we're done. All you need to do now is plug in the equation. And like I said, this is something you can give this to an 8th grader now and say, hey, I've done all this work for you. All you need to do is put in these numbers in the calculator and plug these out for me. So all the hard work is done. Doesn't mean there are not opportunities for mistakes. There still are some opportunities for mistakes. And you do still need to be careful when you're doing the computation, but the conceptual work is done. Okay, so once again, my recordings are going longer than I had expected them to. So this might be a good time to take a break and make certain that you have understood everything that comes up to this point. So the equations that we just saw that govern one charge, take a look at those and make certain you understand where they come from, because what we're going to do in the next part depends exactly upon those. So break time, pause, go back, get yourself a cup of tea, have a cookie, and when you're ready, go ahead and continue on this video for part 2. In part 2, what we're going to do is we're going to take the result we had for 1 point charge, and we're going to extend that to, we're going to use that to determine what the electric field is for the infinite plane. And that is coming up as soon as you continue. All right, so now let's go ahead and do a slightly different problem. Instead of doing this with one charge, let's do this. Let's replace that one charge with a plane of charge that extends in every direction, not every direction because it's just a plane, but it takes up all x, y space. So from x equals minus infinity to x equals plus infinity, from y equals minus infinity to y equals plus infinity, this plane covers the entire universe. And we are going to measure, we need one more bit of information. It's not just a plane, it is a charged plane. And the charge per unit area is sigma. And this will just be some number, 6 nanocoulombs per meter, per square meter. It'll just be something like that. Okay? All right. So now, what are we going to do? Well, how would we do this? Well, first of all, we're going to use Coulombs Law, so we know that. But secondly, I mean, you can't just look at this and use Coulombs Law. You can't just look at this and say, oh, I know somehow I'll pretend this whole thing is a point charge and there's only one distance or something like that. You can't do that. What do you have to do? You have to consider every little spot in this. So what we're going to do is we're going to consider a little spot like this, and we're going to, I lost my cursor. Oh, I know why I lost my cursor. Okay, so we're going to consider a little spot like that, and let's just go ahead and say this happens to be at minus x, minus y, and 0, 0, 0, and z sub p. And so this might look a little familiar right now, because what we're doing is the exact same thing we did for a point charge that was there all by itself. And so we could do that exact same thing an infinite number of times, going all the way out to minus y, all the way out plus y, all the way out minus x, all the way out plus x. And we could do this and we could add these all up together. But that is way too tough a job. And this is why we use the tools of calculus. And what we are going to do is, rather than consider this as as an E field in and of itself, we're going to consider the little tiny contribution of the electric field due to this little tiny spot right here. So we're going to look at this dE, a little tiny change in the electric field, or a little tiny contribution to the electric field from a little tiny piece of charge. Well, look at the geometry here and look at this equation and say, well, what do we have left to know? We've done this geometry already. We did this when we were considering this a point charge. We know what R is. We know what R hat is. The only thing left is this dq. So let's take a look at, I'm reminding us that we know what the R squared is and what the R hat is. Okay, so now that we know that, let's go ahead and figure out how we're going to get that dq. Well, we're going to look at this tiny little spot, and we know it has sigma charge per unit area. Well, what's the unit area of some tiny little spot? It's just dx by dy. So dx and dy, remember, are just infinitesimal little changes in dimension. So we're looking at this infinitesimally small amount of area, but the amount of charge on it is the charge density times the area by definition. Now, I apologize, my dx and dy are not the lengths of my little square, but that's what they're supposed to be. So we've got a little dy here and dx in this direction. So now we know what dq is. Now we know everything in this equation. We're almost done with the physics. We know that dq equals sigma dx dy. We know that, and now what we want to do is we want to get the total of the electric field, and we're going to do this via an integral. So there's our integral, and what it ends up being is an E total at Z sub P, our location, is going to be equal to K dq over R squared R hat, and the integral of that. I pulled the K out because it's constant, and we'll also pull a couple other constants out in a minute because we know that sigma is also a constant. So we have replaced now the dq with sigma dx dy. So now all we need to do is this integral. We know R hat, we know R squared, we know K, we know sigma. We could almost say we're done with all the physics, but we'll go ahead and take it one more step. There's one step that you can think of it physically or can think of mathematically, and we're going to kind of do it both ways. So the exact same expressions we had for the point charge that are in the xy plane, those are the exact same expressions we have here, except now they are part of an integral. We're going to add them up all throughout all x and y space. So this is the exact same expression, except we have now we now have this integral that goes from minus to plus infinity in the x coordinate. So this is our e sub x, this is our e sub y, this is our e sub z. So let's just go ahead and look at those a little bit more closely. Well, first thing to think about is, you guys, when you think about this point that's above this plane, you guys all know that there's going to be a component of the force in this direction. It'll be either this way or this way, right? Depending upon the sign of the charges. So it'll be, or the sign of the charge, I guess. It'll go either this way or this way. So, but because we're above an infinite plane and we're going from minus infinity to plus infinity, because we're doing that, we know for every component over here that pushes a little bit this way, there's going to be a component over here that pushes a little bit that way. And what are they going to do? They're going to cancel out because we're going the same infinite distance in each direction. So just thinking about it that way, we know that this e sub x is going to be 0. We also know the e sub y is going to be 0. So physically, we can think about those and we say we don't even need to do those integrals. However, you can also just take a look at the integrals as well. So let's look at the denominator of this integral. So this denominator, for x, positive or negative, this is going to be a positive number. So this for x and y. So this will always be a positive number. But look at what we have up here. For every positive, you know this is symmetric. You can look at it and see it's symmetric. For every positive number we have here, for every point on the positive x-plane, we're going to have one on the negative x-plane that exactly cancels it out. So you can look at it either physically or mathematically and you say, you know what? I know that's equal to 0. I also know that's equal to 0. And then this leaves us with this. Now, for this one, we know that this quantity here is always positive, and there's nothing here in the numerator which is going to change from positive to negative. So this is I forgot the right mathematical term for it. An even function. There we go. That was hard. Okay, so this is an even function. So because it's an even function, it is going to give us some finite value. Now, at this point, like I said, if you're really into this, you can solve this with trigonometric substitution, but you can also just look it up in the handbook. You've got to play around a little bit. So what you might do, for example, is you might do the x integral first. If you do the x integral first, what you would do is you just replace this with a constant. You say this is x squared plus alpha to the 3/2. And then you would then look that up in a table or use your Wolfram alpha or whatever you want to do. Or like I said, trigonometric substitution works just fine. You can do the exact same thing that the book does for the line charge. You can do that here. Then once you're done with that integral, you then say, oh, you're going to get an answer that's in terms of this alpha that you made up. And then you say, well, I know alpha is y squared plus z or y squared plus some other number. So we just say y squared plus alpha in whatever the answer is to the previous integral. And then you do that integral in y. And each of those are from the minus infinity to plus infinity. So you do that, and you just, it's amazing how we have taken this infinite sum, which would have been incredibly difficult to calculate without the tools of calculus. And the answer is, it just all turns out to be 2 pi over z sub p. That's the answer. And like I said, if you want to work it out various ways, there are ways you can do it, but the answer is 2 pi over z sub p. You plug that in, and we're going to also remember here, I'm reminding you that k is 1 over 4 pi epsilon 0. And your book gives you a value for k, but it also gives you this value for epsilon 0. At some point, we're going to, maybe really soon, yeah, probably really soon, we're going to stop using k altogether, and we're just going to use 1 over 4 pi epsilon 0, because it turns out epsilon 0 is involved directly in more different measurements than, and more different calculations than k is. So we end up with this. We do our simplification, and we get this answer. E sub z equals sigma over 2 epsilon 0. Now, look at that. And notice if there is something unusual about that. What happens as you get further away from this infinite plane of charge? What happens to the electric field strength? Nothing. That's unusual when you consider that if it was a single charge, it would be weakening as 1 over r squared. So something weird there. And one way to think about that is, you have, if it was one charge here, exerting a force here, it would fall off as 1 over r squared. But kind of the further you get from here, the more these charges that are far away start to influence this charge up here. So when they're here, they're just kind of pushing almost right. So if I have some point that's right at the plane, then these points that are way out here are coming almost directly in like that and doing nothing going this way. But as they get higher, they're still going to cancel in this direction, in this dimension, but they will add a bigger value in this dimension. And so because of that, and because it is an infinite plane, we end up with a field strength that does not change as you get further away from the plane. Now, you might be saying, well, what the heck use is this? An infinite plane, there's no such thing. Turns out that for some very real situations, this is actually a very good approximation to the strength of the electric field at a metal plate. Okay, so what I'd like you to do is take a look at example 21-12 in your book and tell me how this, what we have just done, compares to what they have done for example 21-12. All right, that's it. Good job.